In this video, we'll be looking at how to draw basic Lewis structures for simple molecules. So before we start learning how to draw Lewis structures, we need to talk a little bit about what Lewis structures are and what are they trying to tell us. Lewis structures are a very basic representation of the bonding and the valence electrons in molecules. So it gets at the bonding, where are the electrons? We get a little bit more detail about those very key electrons and what's happening with them. So we need to talk for a moment about valence electrons. So valence electrons are those electrons that are farthest away from the nucleus. We care about these that are farthest away from the nucleus because these are those that are going to be involved in bonding. The ones that are very, very close to the nucleus, they're not easily shared with other atoms, so they're not involved with the bonding. We care more about these valence electrons that are farther away from the nucleus that end up being more involved with the bonding. One of the first things we have to be able to do is to be able to count valence electrons. And it's very easy to count the valence electrons because the valence electrons end up matching the group numbers using the old numbering system. This is the reason why we're using the old numbering system, is because the old numbering system provides you some very useful information right away. And that information is how many valence electrons does that atom start with? And it's very easy. Things in group 1A, 1 valence electron. 2A, 2 valence electrons. 3A, things in group 3A, will have 3 valence electrons. And this will go on and on and on. Group 4A would have 4. Group 5A would have 5. Group 6A would have 6. Group 7A would have 7 valence electrons. And that's why everybody still uses the older numbering system, because it gives you very quick and easy access to how many valence electrons you're looking at. You can kind of see here with a picture of the periodic table that we're using the old numbering system. 1A1, 2A2, group 3A3, 4A4, 5A would have 5 valence electrons. Everything in group 6A, oxygen, sulfur, selenium, 6 valence electrons. 7A, fluorine, chlorine, bromine, iodine, 7 valence electrons. That's why the old system gets used. If you're looking at the newer system, well, group number 15 doesn't tell you anything particularly useful in regards to valence electrons. But saying that something is in group 5A, that gives you some instant useful information that you can take advantage of. And that's why we use the older numbering system. So to draw Lewis structures, you will have to have access to a periodic table. I'll kind of go through the rules for writing Lewis structures. So what I would highly recommend is to pause the video right here and pull up the PowerPoint slide that has this on it and kind of look at it while you're watching the video. Because what we're going to be doing in this video is we'll be doing a series of examples. And those examples follow these rules. So the easiest way to kind of see the example at the same time kind of following along the rules is to have them both open. So I recommend opening up the PowerPoint presentation to this slide, having this open while you are also watching the video of us doing the examples, because we're going to go through and we're going to use the examples to illustrate these steps. So I think it's easiest if you have both of those available to you, that you're able to look at these rules at the same time we're going through and talking about each one of these specific examples. So highly recommend you pause the video, pull up this slide on the PowerPoint, and then continue the video so we're able to kind of go through some specific examples of how this works. So the first example we want to do is CF4. And the very first step in writing a Lewis structure is determining the total number of valence electrons that you have. If Lewis structures show the bonding and the valence electrons, well, we need to know how many we're dealing with. Well, it's a pretty straightforward process to figure out the total number of valence electrons. In this molecule, the total number is going to equal the sum of what each atom is bringing in. So when we have CF4, we have 1 carbon and 4 fluorines. Now to figure out the valence electrons, here's where we would look at the periodic table. Carbon is located in group 4A. That's going to mean 4 valence electrons. Fluorine is located in group 7A. That means each fluorine is going to contribute 7 valence electrons to the molecule. If we total all of those up, we would get 32 valence electrons. And it's important to do this step because we know our final structure needs to represent all 32 of these valence electrons. Our next step is to determine what the central atom is. And to determine the central atom, what we want to do is generally it's going to be the first atom listed. These molecules don't come in linear chains where everything's just hooked end to end. Instead, most of these small molecules we're dealing with will have one central atom and then the other atoms surround that one central atom. That central atom kind of serves as the hub. So that's why it's so important to identify. Usually it's the first atom listed in the formula. There's some exceptions to that. Hydrogen is one of those exceptions. So we look at this formula. We're going to put our carbon in the middle of our structure. And we're going to place the fluorines around the carbon. It doesn't matter exactly how you place them around as long as they are surrounding that central atom. So we determined what the central atom was. It was the first atom listed for this one. Our next step involves actually starting to form this molecule together. What's holding these different atoms together? So our next step is to make a single bond connecting each outer atom with that central atom. So the way we represent bonds in Lewis structures are with lines. And to show that they're being shared, that line gets drawn between the two atoms. So if I'm trying to show that there's a bond between the carbon and fluorine, we represent that with a line. Each line I represent between the carbon and each fluorine is that bond. So I'll kind of write this on the side, but when we see a line in a Lewis structure, what that means is that is a bond. And what a bond really means is that 2 electrons are being shared. So every time you see one of those lines, that represents 2 electrons being shared. So I have 2 electrons being shared between the fluorine on the left and the carbon. 2 more electrons between the fluorine on the top and the carbon. 2 more electrons being shared between the fluorine on the right and the carbon. And 2 electrons being shared between the bottom fluorine and the carbon. And we still don't have 32 electrons in this molecule, so we need to get some more electrons in here. This is where the next step comes in. The next step involves adding lone pairs. And the way you add lone pairs is you complete an octet of electrons around the outer atoms. You think about octet. Octet means 8. And what that means is that most of these small molecules that we're dealing with, the atoms generally will have 8 electrons in their general area. So we fill in the remaining electrons around the outer atoms in the form of lone pairs. And the way we represent lone pairs in Lewis structures are with pairs of dots. These lone pairs always come in pairs. And these are not being shared. These will belong exclusively to that outer atom. So if I look at the fluorine on the left, how many electrons are currently in its area? Well, currently in its area, I have 2 from the bond. In order to get up to 8, I need to start adding lone pairs. How many lone pairs? Well, I would need to start having 3 lone pairs. Here's 1 lone pair. Here's another lone pair. Here's my 3rd lone pair. Now I'm up to 8 electrons there. 3 lone pairs will go on each outer atom. Do the same thing for the fluorine on the bottom. Each dot represents an electron, but they're always coming in pairs. That's that lone pair. 1 lone pair is 2 electrons. Do the same thing for the fluorine on the right. 3 lone pairs around that one. Fluorine on the top, 3 lone pairs. Notice how I'm not putting these dots between the fluorine and the carbon. Anything that's between the fluorine and the carbon represents something that's being shared. These aren't being shared. These belong exclusively to fluorine. So when we think about it, every time you see a pair of dots, when we see a pair of dots, what that really represents, that's how we're representing these lone pairs, by pairs of dots. Now the next couple steps we're going to do are the most important. Even if you've learned Lewis structures before, maybe thought about them a little bit in a different way, I encourage you to always do these next 2 steps. These next 2 steps pretty much guarantee that you are going to do the problem correct. There's 2 things that are going to be true in our Lewis structures. One, if we have the correct Lewis structure, we will have 32 electrons. If we don't have 32, it is guaranteed to be incorrect. It has no chance of being correct. So let's see if we have 32 electrons in here. Let's kind of count them out. I'll kind of show my counting with the highlighter here. So let's count up our 32 electrons. 2, 4, 6. Remember, this line is a bond that represents 2 electrons. 8. This bond is also 2 electrons. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's good. We have 32 electrons. That's what we want. That's the first check. That check passed. I just kind of erase the highlighter. Then we can go to our second check. Our second check that we want to always do is we're checking for this octet rule. Some atoms, like hydrogen again, aren't going to follow the octet rule, but most atoms will. So what we want to do is we want to stop and see, are there 8 electrons around each one of our atoms? Are there 8 electrons in the general area of each atom? So to kind of count these out, I will kind of circle in blue here. We look at this fluorine on the left. Do we have 8 electrons? Well, we count the lone pairs, the electrons in the lone pair. 2, 4, 6. 2 from the bond make 8. If I kind of look at the electrons around the fluorine on the bottom, do I have 8 electrons there? Sure, I can count them. Here's my 2 from the lone pair, another lone pair is 4, another lone pair is 6, and the bond is going to make 8. So I have my 8 there. Do the same thing with the fluorine on the right. We will kind of say, are there 8 electrons in that general area? Yes, count them out. 3 lone pairs at 2 electrons each, plus the 2 from the bond, give us our 8 electrons. And finally, the fluorine on the top. Do we have 8 electrons in here? Yes. Count out 3 lone pairs at 2 each for 6. 2 electrons from the bond make 8. All of our outer atoms have that octet of electrons. They have 8 around it. Kind of erase our grouping and counting. There's one last thing we need to check. The last thing we need to check is we need to check the central atom. Do we have 8 electrons around that central atom? And I'll count them out. 2 from the bond, 2 from this bond make 4, 2 from this bond make 6, 2 from this bond make 8. I do have 8 electrons around that carbon. So both of our checks worked out for this. Our total number of electrons were correct at 32, and all of our elements, all of our atoms, both outer and central, had 8 electrons around them. For these small molecules, straightforward molecules we're doing, anytime both of those checks work, you are guaranteed to have the correct structure. And that's why it's so important to do those checks. You can check to see if you have the right structure very, very easily. So now we want to look at another example. We're going to go through the steps the same way we did before. First thing we want to do is count those valence electrons. So look at our parts. What do we have? We have a nitrogen and 3 bromines. We would use the periodic table to find them on the periodic table, figure out what group numbers they're in. Nitrogen is in group 5A. That's going to give us 5 valence electrons. Bromine is in group 7A. So each bromine contributes 7. So our sum total would be 26 valence electrons. That's our first step. Next step is we want to identify the central atom. Usually it's the first one listed. So we're expecting nitrogen to be our central atom here. We want to get nitrogen as the central atom and put the bromines around that central atom. It doesn't matter how you arrange them around the nitrogen. You can put them equally spaced. The one I put on the left, you could put on the top. The one I put on the bottom, you could have put on the top. You could arrange them all nice and symmetrical and evenly spaced. It just doesn't matter when you're drawing the Lewis structures. Those are all okay. We have our central atom and the outer atom. Now we're looking at there has to be something connecting these pieces together. So now it's time to draw bonds, one from each outer atom to the central atom. So we'll make a bond from the outer bromine to the nitrogen. Remember, our lines between represent bonds. Bond between the bromine on the bottom and the nitrogen, the bromine on the right and the nitrogen. So now we have our bonds. Our next step is we're looking to complete an octet of electrons around the outer atoms. So right now, each of the bromines has 2 electrons in their vicinity, the 2 electrons from the bond. So that means in order to get up to 8, I'm going to need 3 lone pairs. So on each outer bromine, I'm going to make 3 lone pairs. There's 1 lone pair, second lone pair, third lone pair on the bromine on the left. Bromine on the bottom will get 3 lone pairs. Remember, these always go in pairs, and we're not putting them between the bromine and the nitrogen because that would represent that they're being shared, and they're not. These electrons belong exclusively to the bromine. Bromine on the right still needs lone pairs, 3 lone pairs to bring its total number up to 8. So now we completed the octet on the outer atoms by adding lone pairs. Now it's time to do our checks. Remember, the first check was, do we have the correct total number of electrons? Remember, we're looking for 26 electrons. That's what we totaled up in that first step. Do we have 26? Well, let's count them. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We don't have the correct number of valence electrons. What that means is this is not the correct structure yet. We're not done yet. We're short electrons. We're not even going to bother doing the octet rule check. We have bigger problems to solve. You solve the biggest problem first. The biggest problem is we don't have the correct number of electrons. We're short electrons. So in order to fix that, we kind of go down our checklist of steps, and now we're kind of at the bottom. We're beneath those checks because one of those checks failed. Well, we have ways of fixing that. When you're in this situation, you're short electrons. You need more electrons in the structure. And that's what we saw. We saw that we have 24 currently drawn in our structure. We need 26. So when you need more electrons in your structure, that is when you may start putting lone pairs on that central atom. So we need 2 more electrons on that central atom. And that's the only place they can go. So we're going to make 1 lone pair on that central atom. Now, just because you're at a step farther down than the checks, the last thing you should always do in a problem that involves drawing Lewis structures is to go back and make sure both of those checks work. When both of those checks work, remember, you're guaranteed to have the correct structure. So let's go back and do both checks. 26 electrons. Do we have 26 electrons now? Let's count them out. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Yes, we do have 26 electrons now. So that's good. We fixed that problem. Remember, we didn't initially do the check of the octet rule because we had bigger problems to solve at that point. We weren't even worried about the octet rule at that point. Well, we still have to check to make sure the octet rule is working. So we want to go back and check the octet rule. Are there 8 electrons in the vicinity of each atom? So around the bromine on the left, do we have 8 electrons in its vicinity? Well, count them up. 2, 4, 6, 8. We have 8 electrons, so that's good. We need to do the same thing for the other bromines. The bromine on the bottom, you would count those up. 2, 4, 6, 8. We do have 8 around that bromine as well. The bromine on the right, do we have 8 electrons around that bromine? Remember, that bond counts as 2 electrons. So do we have 8? Yes. 2 from the bonds, 6 from the lone pair. So we do have 8. Remember, we're not just checking the outer atoms, we're also checking that central atom. So we need to look around this nitrogen. Does this nitrogen have 8 electrons in its area? Well, count them up. 2 from the 1 lone pair, that's 2 electrons. Now the bonds, each bond gives us 2 electrons. So we're at 2, 4, 6, 8. We do have 8 electrons around all of our atoms. So being we have 8 electrons around all of our atoms, both of our checks worked. Remember, when both of your checks work, you are guaranteed to have the correct Lewis structure. So this example showed kind of when you go through that initial sequence of steps, if you don't have enough electrons, it's at that point that you're adding lone pairs to the central atom. You don't want to start off adding lone pairs to that central atom. You wait and see if you need them in order to get more electrons into the structure. Do another one. We're looking at SF2 for this one. And remember, the first step in doing a Lewis structure is counting up the total number of valence electrons. So here we have sulfur and 2 fluorines. Sulfur, when we look at it in the periodic tables in group 6A, Fluorine is in group 7A. So we total up the number of valence electrons, we would be looking at 20 valence electrons. Next step is to determine the central atom. Usually it's the first one listed in the formula. So we're looking at sulfur. Fluorine would be the outer atoms, so we'd have two fluorines. Remember, it doesn't matter. I could put them left, right, top, bottom, top and left, top and right, bottom, left. Doesn't matter as long as it's clear what the central atom is and what the outer atoms are. We need something holding these various pieces together. So you're going to make a single bond between each outer atom and the central atom. So a bond between fluorine on the left and the sulfur, and a bond between the sulfur and the fluorine on the right. Remember, those lines represent that bond, 2 electrons being shared. Our next step is to complete the octet on the outer atoms. Each outer fluorine currently has 2 electrons in its area, the 2 from the bond. To get up to 8, we would need 6 more electrons. That would be 3 lone pairs. So we're going to make 3 lone pairs around each one of our fluorines. Next up is to check for our total number of electrons. We're looking for 20 total in our structure. That's what we tallied for the first step. Do we have 20 in our structure? Well, let's count them up. 2, 4, 6, 8, 10, 12, 14, 16. We do not have 20 in our structure. We only have 16. So we're not the correct structure yet. We're in the same situation we were in the previous problem. We're short electrons. We need to put more electrons into our structure. So when we need to put more electrons into our structure, where do they go? It's at this point that we can start making lone pairs on that central atom. Here we're short 4 electrons. That would be 2 lone pairs. So I'm going to add a lone pair on the top and a lone pair on the bottom to put 2 lone pairs on that central atom. Now again, we made some changes. We think we're good, but there's no reason not to go back and double check just to make sure you're good. Check your total number of electrons again. Make sure you have 20 in there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 20 total electrons. That's good. Remember, we didn't check the octet rule the first time through because we had bigger problems to solve. We had to solve the getting the correct number of electrons problem. We still need to check the octet rule. Remember, to check the octet rule, we're looking around each atom. Are there 8 electrons in the general area around each atom? Fluorine on the left, yes. Lone pair gives 2. Other lone pair gives 2 for 4. 2 more from a lone pair, 6. Bond is going to make 8. We look at the fluorine on the right-hand side now. If I look at the electrons in its general area, do I have 8 electrons around that fluorine? Well, 2 from the bond. Lone pair makes 4. Another lone pair makes 6. Last lone pair makes 8. So both the fluorines are good with their octet rule. They have 8 electrons in their vicinity coming from the 1 bond and the 3 lone pairs. But what about the sulfur? We still have to check that central atom out as well. So when we look at the sulfur, what kind of electrons do we have around that sulfur? Well, do we have 8 in its general vicinity? And the answer is yes. 2 from the bond, 2 from this bond make 4, 2 from this lone pair make 6, 2 from that lone pair make 8. We have 8 electrons around the sulfur. So here, again, we're in the situation we had to add lone pairs to the central atom. In this case, we had to add 2 lone pairs. But that gave us not only the correct number, it also gave us the octet rule around everything that needed the octet rule. So once again, both of those checks worked for us. When both of those checks work, remember, you're guaranteed for the molecules we're working with to have the correct structure. You've seen in the rules that hydrogen has been an exception to some of the rules we've been following. I want to do a couple of hydrogen examples to kind of illustrate those rule changes that exist. Well, first up is just counting up the valence electrons. We have one carbon, 1, 2, 3, 4 hydrogens. Carbon resides in group 4A for 4 valence electrons. Hydrogen is in 1A, so each hydrogen will contribute 1 valence electron for a sum total of 8 valence electrons. So we have 8 valence electrons we're going to need to put in here. Determine the central atom. Usually it's the first one listed. Also, hydrogen can't be the central atom. Hydrogen can't handle it. Well, carbon's first, and we know it can't be hydrogen, so we're going to put our carbon in the middle. That means hydrogen will be the outer atoms. We'll place hydrogens around the carbon. There has to be something connecting each outer atom with that central atom. So we're going to make a bond between each outer atom and the central atom. Now it's at this stage that you would normally complete the octet on the outer atoms. Hydrogen, though, doesn't get an octet. Hydrogen can't have 8. It's too small to be able to handle 8 electrons. Hydrogen follows a different rule. Hydrogen follows what we would sometimes call the duet rule. Hydrogen gets 2 electrons around it. You can see each hydrogen already has 2 electrons around it from the bond that it's involved with the carbon. So when you have hydrogen as the outer atom, you're not adding any lone pairs to that hydrogen. So you're kind of skipping that step, and now we can go right to our checks. Hydrogen doesn't get any lone pairs around it. Now we can go to our checks. 8 total valence electrons. Do we have 8? 2, 4, 6, 8. Yes, we have 8 electrons in our molecule. Do we have an octet? Well, hydrogen doesn't follow the octet rule. Hydrogen follows what's called the duet rule. That's 2 electrons. Hydrogen on the left, it has 2 electrons, the 2 from the bond. Hydrogen on the bottom, again, won't have 8. Hydrogen follows the duet rule, has the 2 from the bond. It's good. Hydrogen on the right has the 2 from the bond. It's good. Hydrogen on the top has the 2 from the bond. It's good. So our hydrogens are okay. We do have to look at the carbon, though. Even though hydrogen is not following that octet rule, carbon still absolutely has to follow that octet rule. So do we have 8 electrons in the area around carbon? Well, let's count them up. 2, 4, 6, 8. We have 8 electrons around that carbon. So no lone pairs at all in this molecule. Both of our checks worked out. Remember, we checked for our total of 8 valence electrons. We also checked for the octet rule. Well, carbon would follow that octet rule. Hydrogen does not. Hydrogen followed the duet rule, and it has its duet of electrons. So both of our checks worked. That means we have the correct structure. And you always want to do these checks. I know they kind of seem like they take a little bit more time, but it's pretty much a guarantee that yes, you did this problem correctly, and it's a way you can know before moving on to something else that yes, this is what I have, and you know, there's no worry about did I miss something. If the checks work and you counted correctly, you definitely have that right structure. We'll do another example of that has hydrogen in it. This time H2O, water. Well, first up is to count up the total number of valence electrons. I have 2 hydrogens, 1 oxygen. Hydrogen on the periodic table is in group 1A. Oxygen on the periodic table is in group 6A. So we're looking at a sum total of 8 valence electrons again. Next up, determine the central atom. Usually it's the first one listed, but hydrogen can't be the central atom. Well, hydrogen's the first atom in the formula, but hydrogen can't be the central atom. So if it's not hydrogen, it had better be oxygen. So we're going to make oxygen our central atom because hydrogen can't be the central atom. We're going to put the hydrogens around that central atom. Now in reality, this is not how the hydrogens are arranged in a water molecule. They don't form a straight line. It's not a linear compound. It's actually bent. But we don't need to worry about that three-dimensional nature of water in terms of just writing the Lewis structure. So I'm just going to kind of keep it as linear, even though we know in reality it's not a linear molecule. For Lewis structures, you're not trying to convey three-dimensionality on its own. So we can just kind of go through the same process we have been doing and not worry about that at the moment. So we're going to make a bond between each outer atom and the central atom. There has to be something holding these different pieces together. Your next step would be to complete an octet of electrons around the outer atom, but remember, hydrogen doesn't get an octet. Hydrogen only gets a duet. It can't handle any lone pairs. So we're not adding any lone pairs to hydrogen again. Now we can start doing our checks. We're looking at 8 valence electrons. Do we have 8 in our structure? Well, 2, 4. We have 4 in our structure. So right away, we're not at the correct structure yet. What do you do when you're short electrons, when you need more electrons? Well, when you need more electrons, that's when you can start adding lone pairs on that central atom. So I'm short 4 electrons. That would mean 2 lone pairs. So I'm going to put a lone pair on the top of the oxygen and a lone pair on the bottom of the oxygen. Now again, go back and do your checks. Pretty much guarantee yourself that you're able to do this, that what you did is correct. So do your checks. 8 valence electrons. Do we have 8? 2, 4, 6, 8. We have 8 valence electrons. That's good. Are we following the octet rule? Well, check the octet rule out. We know hydrogen doesn't follow the octet rule, but that hydrogen on the left follows the duet rule. It'll have 2 electrons, and it has 2 electrons, the 2 from the bond. The hydrogen on the right, again, that's going to follow the duet rule. Hydrogen doesn't get 8, it only gets 2. Does it have its 2? Yes, the 2 from the bond. Now, even though hydrogen is not following the octet rule, oxygen still needs to follow the octet rule. So let's look at the oxygen. Do we have 8 electrons in the area around oxygen? Yes, we can count them up. 2, 4, 6, 8. We have 8 in its general area. So again, both of our checks worked out here. We have the correct total number, and we also have the octet rule around things that need to have the octet rule followed for. So this is our structure for water. 2 lone pairs on that central oxygen. We have the correct total, everything. Both of our checks worked out. This is our correct structure. We have one last molecule that we want to look at. This is SO2. This is sulfur dioxide. You might be familiar with it. It's a contributing gas that can help make acid rain. So it's kind of an important environmental thing to be on the lookout for. So again, count up your valence electrons. That's the first step. Sulfur is in group 6A for 6 valence electrons. Oxygen is also in group 6A for 6 valence electrons. So our sum total is we're looking at 18 valence electrons in our structure. Next up, determine that central atom. Usually it's the first one listed. So we're going to put sulfur in the middle. We're going to put oxygens around that sulfur. We have 2 oxygens that we need to place around. Next up is we would make a bond between each outer atom and the central atom. So we'll make our bond in here. Next step would be to complete the octet of electrons around each outer atom. That would mean 3 lone pairs around each outer atom. So we're going to put 3 lone pairs around each outer atom. Now we want to check and see where we're at. We're looking for 18 electrons. Do we have 18? Well, let's count them up. 2, 4, 6, 8, 10, 12, 14, 16. We don't have 18, we only have 16, so we're short 2 electrons. Well, we've seen from previous examples what we should do when we are short electrons. Whenever we are short electrons, those can be added in, those extra electrons we need, as lone pairs on that central atom. So we're short 2 electrons. 2 electrons would be 1 lone pair. We're going to add 1 lone pair to that central sulfur atom. Go back and do your checks. Do we have 18 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, we have 18, so that looks good. Now we need to kind of check our octets. So to check our octets, we need to look around each one of our atoms to see if we have 8 electrons in its vicinity. Around that oxygen on the left, do we have 8? Yes, 3 lone pairs, 2 electrons per lone pair make 6, 2 from the bond make 8. Same thing with the oxygen on the right, we would have 8 electrons around that oxygen, so those 2 are looking good. But look at what happens when we look at the sulfur. When we look at the sulfur, how many electrons do we have around the sulfur? We have 2, 4, 6. We don't have the octet rule. We have a different problem. Now you may be thinking, okay, well, I need more electrons, I'm just going to throw in another lone pair on the sulfur. You can't do that. Let's look and see what would happen if you tried to do that. If you tried to do that, and I'll do this in red because this is not correct, if you just decided, oh, I guess sulfur needs more electrons, if you did this, you would have a problem. If you count up the electrons here, you would end up with 20 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's not going to get the job done. So we can't just throw in more electrons. This is a different problem than we have faced previously. It's not that we don't have the correct total number. There are 18 electrons in this structure right now. The problem isn't the total number. The problem is the octet rule isn't being satisfied. So being this a different problem, it requires a different solution. For this, we have to keep our 18 electrons that we have, but we need to rearrange them to satisfy the octet rule. And the way you do this is you take from one of the outer atoms, one of the lone pairs, and make another bond with the central atom. So you take one of the lone pairs from one of the outer atoms and make another bond with that central atom. It doesn't matter which outer atom you pick or which lone pair you pick. I'm going to pick the oxygen on the left, and I'm going to pick these lone pairs that I circled in blue. We're going to take these electrons, and instead of these being exclusively oxygens, we're going to move them in and share them with the sulfur. That way they'll both be near the oxygen still to satisfy its octet rule, but now they'll also be in sulfur's area in order to satisfy that octet rule for sulfur. So what I want to do is just draw out this change, what the blue arrows are showing, taking that lone pair and moving them in to form another bond with that central atom. Everything else in the molecule is going to stay the same except for that specific change that got made. So we're going to leave everything else alone, except now we're going to add another bond. All of the lone pairs that weren't involved in this change will also stay the same. We're going to draw these in here. So now we just made a bunch of changes. Remember, you have a way to determine if you have the correct structure or not. Those two checks will tell you this is correct or no, this is not correct. Let's go through and do those checks again, being we just made a bunch of changes. Do I have 18 electrons? Let's count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, I still have 18 electrons. That check is still good. Now, do I have an octet of electrons around each of my atoms now with the fix that we employed? Well, let's look at the oxygen on the left. Do I have 8 electrons in its area now? Well, lone pair, that's 2. Other lone pair, that's 4. One bond makes 6. One bond makes 8. We now have a double bond, 2 bonds between that sulfur and that oxygen. 2 electrons are being shared in each bond. 4 total electrons are being shared, that means. But I have 8 electrons around that oxygen now. If I look at the oxygen on the right, do I have 8 electrons in its area? Well, count them up. 2 from the bond, now lone pairs 4, 6, 8. Yes, we have 8 electrons around that oxygen. So that one is good. We still have to check the sulfur. Remember, sulfur not having an octet is what initially caused this problem. Did we fix that problem? Well, let's look at the sulfur. So if we look at the electrons around the sulfur, do we have 8 now? Well, 2 from the bond on the right, 2 from the lone pair make 4. Remember, I have 2 bonds between the sulfur and the oxygen on the left, so 6, 8. I have 8 total electrons around that sulfur. So now this sulfur is good. We fixed this problem. So being we fixed that problem, both of these checks worked out. We have 18 total electrons in our structure, and each of our atoms is following that octet rule. There are 8 total electrons around each atom. That means we are guaranteed that this is the correct structure. So this step of moving a lone pair from an outer atom to the central atom, you're only employing that when you're not hitting an octet around the central atom, but you still have the correct number. Remember, there's 2 different problems you can have. You don't have enough electrons. That's what we saw in some previous examples. This one shows what happens when you have the correct total number of electrons, but they're not arranged properly. You sometimes have to do a little bit of rearranging. And the way you do that is you take a lone pair from the outer atom and make an additional bond with that central atom.